All right. All right. Well, good evening, everyone, and welcome to the October meeting of the RASC Ottawa Centre. I'm your host, Paul Klauninger, and extend greetings to all of our club members and visitors alike, and with a special welcome to RASC members watching us on Zoom from other centres across this wonderful land of ours. We have a special program for you tonight with a couple of really good presentations and a lot of observations. So I won't dally here, and I'll move us along, provided I can get the pointer to, oops, pointer to work. There we go. Just to let you know, we are recording this meeting, this webinar, and it will be available on our site. In addition to our usual recording, our first presentation will also be recorded. This is a special presentation by Doug and Neil O'Brien and Rob Dick. And it's going to be it's winding up in the museum archives, basically on the topic that they'll be talking about, which is some of the historical imaging and photography and astronomy in general that was conducted at the Dominion Observatory when it was functional as such in Ottawa. So just to make you aware of that, in case you're wondering about the different camera setup. For those of you tuning in on Zoom, just a note that you can use the question and answer function to ask a question of the speaker. Typically, we like to keep those to the end of the presentation. And just a reminder that chat box comments can be seen by everyone. The raise your hand function in Zoom is disabled, though. All right, and we'd like to acknowledge the trust placed in us by our First Nations with their ancestral lands and skies here on our site. Okay, tonight's program, introduction. Dave Chisholm will talk to us about Ottawa skies for October, and then the presentation that I just mentioned regarding the Dominion Observatory. I'm looking forward to this, guys, because I've worked with that the 15-inch telescope, and I'd like to see what it was done with it before it came to the Science and Tech Museum many years ago. We'll then have a break, and then Adam Brown will talk to us about stellar streams in the galactic halo. This will be followed by our observation reports and Richard Taylor's monthly observing challenges. And finally, we'll wrap up with our few of our traditional announcements. Welcome to the new members that have joined us. We've so far had 89 new members in 2025. So welcome everyone, and I hope you are enjoying your stint with us so far. I hope we are delivering a program that you like. Just a reminder too. Actually, I'm probably jumping the gun on this because Andrea is going to talk about it, but we will be launching a survey to the membership. Asking your opinion on how we can tailor the meeting or refine the meetings. We're just trying to get some feedback. Okay, the annual dinner at Algonquin College. I believe Andrea is going to talk to this one. Are you with us, Andrea?
I'm here on Zoom.
There you are.
There I am. Can you hear me?
Oh, no audio. No audio, Andrea.
I have my it's on. I
The
have my
gremlins. The gremlins
it's
are,
on.
yeah.
They can
Chris, we're
hear me
zero on the audio out
online.
here.
They can hear me online, but this isn't
Okay, nothing out here though.
right. Well, I will talk to the people online. The dinner is here at Algonquin College. We're going to have a lovely
Well,
meal
while he's
at
trying to get us past our audio problem there, you can certainly read about it. It concerns our annual dinner coming up in November. Oh, there's Chris doing
hello.
his magic.
This isn't surprising. I often don't get to talk at these meetings. Um,
Well, Andrea's happy.
I think this is like my fourth or fifth technical glitch this year
As you
with
can read,
audio.
it's November the 15th, and it will be held at our usual venue at the Algonquin College. We will have door prizes, special guest speakers. There'll be a cash bar. And the price per person, the bottom line is that it's $65 per person with parking fees and alcohol, obviously extra.
If you're online and listening, what
Negative.
we're going to do is we're going to ask you to send an e-transfer to the treasurer to pay for your ticket, and then CC me with the email so that I know that you
Spouses and
signed
children
up.
are welcome. Delicious dinner options, center awards, and door prizes. There. And just
I'm
a great
also
opportunity to come and celebrate and socialize with your fellow RASC members. It's the dinner is always a good time. They do a great job at Algonquin for us, and it never seems to disappoint at all. So
agree with everything he is saying.
there we
That's it.
go. Yo,
Oh,
Roger.
you hear me now?
We can, yes.
All right. I was going to say, I agree with everything you say. It's a very delicious meal. Um, I've already had some people talk to me about it. So the key is that you have to pay via e-transfer to Cliff, who is our treasurer, and you just send him an e-transfer saying, giving him your name, how many people are coming. The child price is still about $50. So if you have a very small child, talk to me. I'm sure we can figure something out. There are vegetarian options. It is a roast beef dinner, and there is a full vegetarian option, coffee, soft drinks included, and dessert, coffee. The only thing you pay for is your bar and parking. Our special guest speaker, it will be Malcolm Park. He is a Kingston member, and he is going to come and talk to us about his extraordinary remote setup in Chile and some of his explorations of the southern skies. So I'm really excited about that. Next slide, please, Chris. I do want to mention we have two sponsors so far, and so I want to tell you a little bit about them. Astronomy Plus is a astronomy supplier out of Montreal. They have sent me already some really great door prizes, a solar telescope, binoculars, planetary camera, some gift certificates, and they're a really great outfit in Montreal. We don't have a local store anymore. I highly recommend. All my dealings have been really great with Astronomy Plus. Telescope Canada is a retailer out of Toronto, and I use them exclusively when I first started doing imaging during COVID. They have excellent customer support, very reliable, very dependable. So please support our sponsors if you can, so we can have more prizes every year. Next slide, please. As Paul alluded to, you should be getting an email in the next few days with a member survey. The survey is so that we can hear a little bit from you. What do you think of our meeting format? Is it too short? Is it too long? Is it too technical? Is it not specialized enough? We really are looking forward to your feedback. We're trying to decide whether or not we need to change things up or keep things the same. There'll also be some questions about what do you think about the annual dinner? Do you like that format? Do you like the location of the dinner, the meeting venue? So keep your eyes open for that email. You're also going to get an email from me about the dinner. So two emails are on their way, so keep an eye out for them. I do want to also mention in December, we have our annual general meeting where we re-elect board members. We are going to be alternating. We don't elect the full board every year, but there are openings, and you don't necessarily have to be on the board. You can volunteer to shadow a counselor or a director to learn about their position. We desperately need somebody who has IT knowledge, ideally with Google Workspaces. If you know Google Workspace, please call us. And again, we would love, if you're an astrophotographer, you could do social media for us. It's perfect. You have lots of pictures. And I've already had one volunteer for a children's program, and hopefully we can work on that next year. So speak to Oscar, myself, or Dave Chisholm, our past president, if you would like to help out. And you can email us. Our emails are on the website. Next slide, please. Okay, so a bit of an update here on the Chasm events. I don't actually need any more volunteers. You'll be happy to hear. I got a great turnout for tomorrow. If you do have children or people visiting, it is Space Week next week at Chasm. So it is going to be a workshop on how to pick your first telescope. I don't need any more volunteers. However, because they have canceled the October star party for a variety of reasons, but it's not going ahead. So ignore that last bullet about volunteers, but use that email if you want to volunteer and to keep an eye out for all my emails. That's all I have to say. Thank you, Chris, for getting me volume, and thanks, Paul.
Thank you, Andrea. All right. Without further ado, I'll turn it over to Dave Chisholm for our Ottawa skies this month. Okay, thank you, Paul. We're in the process of deeply documenting the processes and procedures here at the museum, so that little glitches like we just have, we now know how to resolve them very quickly. So hopefully moving forward, things will be a whole lot smoother. So let's see what's happening in October. Oh, there we go. So the phases of the moon. And so October the 7th is a full moon. It's also a super moon, means the moon's a little bit closer to the Earth. It was known by early indigenous tribes as the hunter's moon. The game is fat and ready to hunt. It's also been known as the travel moon and the blood moon. This is the first of 3 supermoons for 2025. New moon is on October the 21st. We have 3 meteor showers I'm going to be talking about today. One of them is actually next month, but it occurs before our next meeting, so I'm going to talk about it today. First one is the Draconids meteor shower. It's October 7th and 8th. Guess when the full moon is? October 7th. Good luck with that one. I get these from a particular website where they describe each of these things, and it says here, unfortunately, the glare from the nearly full moon will block most of the meteors this year. Combined with a low hourly rate, it'd probably be best to skip this one, about 10 meters per hour. But it does peak on the night of October 7th and 8th. However, I've got good news for the next one, the Orionids meteor shower. It's a average shower producing 20 meters per hour. It peaks on the night of October 21st, and this is an excellent year for it because the moon is not out. It'll be absent all night long, leaving dark skies for what should be an excellent show. Best viewing will be from a dark location after midnight. And finally, we have the Northern Torrids meteor shower. This one is unique in that there's sort of 2 radiants that are part of this meteor shower. The first one was left behind by asteroid 2004 TG10, and the second stream is debris left behind by comet 2P Encke. But they both are in the same area around the sun, and we pass through them, and it peaks on the night of November 4th and 5th. So it's going to be very close to a full moon as well for that one. Okay, the sun will rise and set. As we're all well aware, the days are getting shorter. That means we can get out earlier and longer with our telescopes, which is awesome. I'm hoping if legislation does go through, they're going to leave the time on standard time and not leave it on daylight saving time. Mercury, here the rise and set times. The first number is the first of the month. Last number is the 31st. And we have the greatest eastern elongation on October the 29th. Look for the planet low in the western sky just after sunset. So it's its furthest distance from the sun at that point. Venus is not visible. It's rising and setting with the sun. Mars is visible at dusk, but it's you got to catch it really shortly before sunset or shortly after sunset. Jupiter is visible in the late evening and through the night. By the end of the month, you'll be able to see it. Well, it's at the horizon at 10:33, so probably around 11 o'clock. Saturn is visible in the evening sky all month. Uranus is visible in the evening, and Neptune is visible through the night. And here is our cartoon of the month. Thank you very much.
Thanks, Dave.
All right. And without further ado, gentlemen, I yield the stage to you. Please welcome Doug O'Brien, Robert Dick, and Neil O'Brien. Here you go, sir.
Okay. The astro images that people take here are fantastic. But back in the 60s and 70s, it was much more difficult when we were using film. What we're going to do here is give you an overview of the role of and historical status and the current disposition of the Dominion Observatory at Ottawa, an overview of the instruments and how we used them, and a description of how film and glass plate photography was done in those days, primarily using the Brashear doublet astrograph at the Dominion Observatory. Now, Canada's always had an important role in astronomy, and this started with the need to establish the borders and of surveying in early Canada. Integral to the establishment of location is the establishment of time. So time becomes a critical, oh, you're quite right. I've been looking down and I haven't done that. So is the establishment of time. Now, we know of Sir Stanford Fleming, 1879. He wrote a paper that established proposed the establishment of time zones around the world. And this worked into a very contentious game of politics that was going on with various nations all trying to establish the prime meridian through their capitals. But eventually, it was established through Greenwich. Now, the prime meridian in Greenwich establishes a zero, but then we need to know where Canada is. And that means we need to know the offset from the prime meridian to Canada to establish a Canadian reference point. The rest of what was going on at the observatory was work on the measurement of the Earth and astrophysical research. Now, what we have to do then is determine where is Canada. Samuel Champlain was one of the first to try to determine the position with his astrolabe, but an astrolabe's only good for latitude. You can't, in the 17th century, you can't do very much for longitude other than to guess. Voltaire called Canada a few acres of snow, that the country covered with snow and ice 8 months of the year. And of course, many people didn't know why we wanted to even bother to know where it was. But it was important for us as a country. So the early surveying, when Canada actually became a country, was to establish our borders and the provincial borders of, first of all, British Columbia, Manitoba, and then Alberta and Saskatchewan. And to do that, we needed to establish a national meridian. So the prime meridian that we saw on the previous slide with that's a plaque on the side of the Dominion Observatory building is in fact established with a transit. But when they did the establishment of the 49th parallel, this was the observatory they used. Notice how they had a nice slot on the roof by just moving a board. And they dragged this across the continent to establish it. Now, the DeVille, who was the Surveyor General, King, and Klotz were the primary people involved in this survey as part of the Survey Commission. And then afterwards, they proposed the establishment of an observatory here in Ottawa as the reference observatory. Now, longitude, which is what needed to be measured because we could easily do latitude. Latitude is just measuring the altitude of the celestial pole, Polaris, or with an ephemeris, the sun angle. But longitude is a time difference from Greenwich. That's much more difficult to establish because how do you determine a time difference? The prime meridian is established with a transit telescope and a very accurate clock. And it's an iterative process between timing with the clock and using the transit telescope. Basically, the transit telescope is a sophisticated astrolabe. And, Champlain would have been proud. The transit telescope points due north, due south. It's in a special wing of the observatory. And there are two buildings which serve as the artificial horizon for the transit and also an azimuth position so that the meridian is well defined. And you'll see one of these here. That's the picture that we have here. Now, there's alternate methods to establish longitude. One is you can measure the angle between a star and the moon. Basically, it's a transit time, but you can measure the angle. And the other is to look at timing with the Galilean moons. And if you combine all of these together, you can slowly iterate to a better and better measurement of position. The Dominion Observatory is still our reference meridian, even though nowadays we do it with satellite orbits and the like, but the line at the Dominion Observatory is our legal reference for Canada. Now, we currently use the North American datum, NAD83, which is a lat-long grid locked to the continent, so that as we get continental drift, the lat-long grid moves. But your cell phone or your GPS will pick up World Geographic System 84, and WGS 84 is dynamic. That is, it's changing all the time. There's a WGS 84 static, which is WGS 84 as of 1984. This is the first observatory called the Cliff Street Observatory. Now, there used to be a street that ran where the Supreme Court currently exists, called Cliff Street, that looked over the cliff behind Parliament Hill. And on Cliff Street, they built this. But it was a terrible place because what happened is the city of Ottawa, or the smaller city, the town of Bytown, was due south of the observatory, so the seeing was terrible. It was close to Parliament, though, and that had its advantage because, well, Parliament is adjacent to the prime meridian, but actually the seeing was important. And there was a transit, a pendulum clock, and a 6-inch telescope in this connected with this observatory. Deville, King, and Klotz then convinced the government to build a proper observatory, the Dominion Observatory. And construction began in 1902, and it was opened in 1905, and it operated until 1970. After it ceased operating, its major instruments were decommissioned and put into the Ingenium Museum. In 2023, based on the work of the people here, the RASC subcommittee on the preservation of the Dominion Observatory, we got the observatory declared a National Historic Site. And the submission was researched and written by Sharon O'Dell and Neil O'Brien, with several other members actively participating in this subcommittee. Up till then, the buildings only had historical status, being designated as being historical buildings because it was designed by the architect David Ewart, and David Ewart was responsible for many of the monumental buildings of that era for Ottawa. So there's the observatory campus. These are federal heritage buildings, but the big buildings are currently used as government offices. So they're used buildings, which means they're maintained. This is a 1966 aerial photo, and you can see some of the buildings there. You can see the North Azimuth building is no longer on this. You can see the South Azimuth building. South Azimuth building, if you a point now, even though that's not going to be there's the South Azimuth building, and there's a line between the South Azimuth building and the transit wing of the observatory. The transit wing of the observatory held the transit, and that line is the meridian for Canada. And the North Azimuth building is off. It was torn down in 1950 when they widened Carling Avenue. The other buildings that disappeared were number 9 and 8 and 3. 3 was a solar telescope we'll show you later, and 9 was a long baseline transit, and 8 was a zenith telescope with a mercury mirror in it, so it was dead vertical, and that they were used to establish the truth of the theory of continental drift. So these are the primary instruments that were at the observatory: clocks, 2 main telescopes, seismographs, magnetometer, gravitometers, the celiostat, which is the horizontal solar telescope, later that long baseline transit, a vertical zenith telescope, and later still atomic clocks for establishing universal coordinated time, which basically replaced the need for the transits. The early clocks were vacuum pendulum clocks. Now, in a vacuum, there's not much resistance to the pendulum other than the knife edge on which the pendulum operates. So it became a fairly accurate clock. This particular picture is the one from St. John's, New Brunswick, not the one that was here in Ottawa, but it's the same clock because they had more than one in different places. And it's down in the bottom, you see the one that is at Greenwich, or was at Greenwich, used at the same time. So how did you, what was done? And unfortunately, you don't see the star behind the picture of the inset, but there's a star up there. And so what you see is the transit and the pendulum clock used together iteratively. You can use time to, you time a star crossing the meridian, and you can use that to establish if you know the position, you can establish the timing, or if you know the time, you can establish the position, and you can do this iteratively combined with some of the other mechanisms that I mentioned, and gradually get your location more and more precisely. So the pendulum clock produced the time signal, and the time signal controlled a time ball that was in downtown Ottawa, and the noonday gun. We still have the noonday gun, but the time ball disappeared when the Parliament buildings burnt down in 1916. There were 2 transits in the transit building, and the big one no longer exists. The smaller one we'll show you. If you want to hear the time signals, then there's the time signals are currently broadcast by the radio station CHU, and the time 3330, 7850, and 14670 kilohertz. It's the US has similar times, and we can compare and contrast different times. You're running out of battery? Okay. Okay, so this is the transit, and the person under it is Plaskett, who was the primary observer at the Dominion Observatory in the early days. You can see the large graduated circles that were used to measure altitude. And you could actually also see a crane in the background, possibly see it, that was used to pick up the telescope, rotate it around, and put it back so that any errors could be canceled because you could reverse it on its mount. And here's the same transit in storage at the museum at the moment. The museum has this very high quality storage facility, so it's safe there, but it's not really open for viewing by anyone. Now we get to the 15-inch telescope. That was the large dome, and it contained this fairly sophisticated instrument for its time. In fact, it was the largest telescope in Canada when installed with a 15-inch lens. Now the lens is called a doublet. We know that as an achromatic lens. We don't think anything of it. But at this era, it was phenomenal to get somebody to grind that big of a lens in crown glass and then in flint glass and have them match that accurately. So that was why they were considered so important. The Brashier's expertise was, he was the telescope maker for professional astronomy at the turn of the 20th century. There was also a spectrograph that you could see in the lower right. It was a very heavy brass and with a thermal box around it and the like, and you'd have to readjust everything on the telescope to mount that thing. The problem with this telescope is it's f/15 and very slow to take pictures. You could do things visually, but taking pictures through it was very difficult. This is the horizontal solar telescope, and these sets of mirrors tracked the sun and sent the beam through a lens system, and the lens system produced a 9-inch solar image. It went through a tunnel and into the basement of the observatory, and there was a 24-foot long spectrograph producing huge spectra that they could measure against, and they could measure 6 points on the limbs of the sun at the same time. And what they were doing was determining the differential rotation of the sun. That was new science at that time. I don't know if they discovered it or they were collaborating to verify, but it was the forefront research at that time. Here's the celiostat in the storage facilities at the museum. And, you know, it's a high quality physical archive, so it's well preserved, but it's not in use at the moment. Now, this telescope was the one that we used a lot. This is the smaller telescope, the photoequatorial telescope that existed in the smaller dome in front of the observatory. This was really a camera. It's fast, f5, and it consisted of an 8-inch doublet or a 6-inch doublet, an off-axis guiding scope, and a Zeiss camera, which you'll see at the bottom there, which is a sky survey camera. And there were 2 prisms, and you'll see one of them in this photograph, one of them is mounted, and is a 15-degree and a 25-degree prism that could be placed in front of the telescope to give star spectra. Here's a photograph of the Pleiades taken with it. Now, the picture isn't great because, well, first of all, it's been sitting in a paper envelope for 59 years, and it's scratched a little bit, and the coloration in the background is just basically the film warping. But exposures for something like this could be 10 minutes to over an hour, depending upon what you were doing, what films you were using. And because there was a clockwork drive, you had to do manual guiding of the telescope. It wasn't just turn it on and take a picture. It was turn it on, take a picture, look through the guide scope, and make adjustments every few seconds to make sure that you compensated for all of the noise in the gears as they moved and the fact that it wasn't quite on and etc. Quite a job of staring through the eyepiece for 10 minutes to an hour while trying to get something like this. Okay, Rob.
Not like the pictures you see here at meetings.
Closer to the mic.
Yep. So there's one thing about this, you have a lot of instruments on a single mount, and that means that the telescope has got lots of you can do a lot of things with it. As pointed out before, you've got the 6-inch f5 astrograph, this 8-inch astrograph. An astrograph gives you very accurate pictures as opposed to just a camera lens, which can have distortion. The wide field camera is on the top, and then we get down on the right-hand side, you see the objective. This is the prism for the 8-inch telescope. This particular one has got both prisms on it simply because this is from the museum, so might as well put them together, saves losing one in a box somewhere. So they mounted both of them. And then on the bottom, you have a finder. So it's actually interesting that even an advanced telescope like this, you're still using a finder telescope. Oops, up here. Right? This is a detailed version of the working, a bit of a close-up of the working end. You can see that it looks very complicated. You don't have push buttons. You have very tactile control over the telescope. And no wonder I became a mechanical engineer, because I found this be really neat. However, it also shows all the weaknesses of 1¼ centuries ago. You have a knob for the 6-inch focus. You have another knob for the 8-inch focus. Now, I'm not sure how this was done. I think there was a lens inside you shifted a little bit, because between the plate holder and the lens, it's pretty well solid metal. So that's about the only way I think you could actually focus it. Now, we also have some other things here. Whoops, did that wrong. Here we are. So you could slowly move the telescope in declination by turning this wheel. It went up to a miter gear that then moved a worm that was in a sector arm that was clamped to the declination axis. How does it get clamped? Well, you have another knob in here with two concentric shafts. Rotate the outer shaft, and you locked the telescope to the declination axis. You did the outside one, then you end up locking the telescope to the right ascension axis. Then you could operate the slow motion control for the right ascension axis, or the polar axis. So concentric shafts made it a little more complicated, especially with 3 in the morning and you start turning the wrong one. This is so it's all very old school control rods and gear trains, and they all had, by just some of the mechanical engineers here, we'll see that there's a lot of chance for backlash in gears, and there was a lot of backlash, which caused a certain amount of grief. Here's an example of something you could do with the telescope, especially the 6-inch, which was specially made to provide a very uniform out of focus image, so that you could do photometry on the star. So here we have this one that Doug produced, and we have a star field. This is not the trapezium in Orion, but what Doug did is he highlighted, he put a slit over the darkest star, or the brightest star, if you think about it, and then do a histogram around it. Now, this star is saturated, so it's flat on the top, not something you want to do photometry to, but the other ones are gray, so you'll be able to get the essentially, I guess you call it this point spread function. You would take the brightness of a disk around the star, then you take another measurement of the brightness of the sky away from the disk with that same aperture, and then you subtract the two and you get the brightness of the star. And as you can imagine, with film, the brighter the object, the difference between a bright object and a faint object wasn't linear. So you had to calibrate this with lots of standard stars. Digital makes it so much easier. The sky survey camera was kind of neat because in those days, going back a century and almost a century, one of the third centuries, you didn't have a very good sky survey. So it was always beneficial to have, or it was beneficial to have a wide angle view of the sky, take lots of pictures of the whole sky to document what the sky was. Now, that's easier said than done. This is a nice camera, but look at the size of the this is held 10-inch glass plates. And it had to be glass because as the telescope moved around the sky, if it was film I guess film, then it would warp and change as you moved the telescope. And it was also changed throughout the night. So at least the glass was very stable. The objective prisms were kind of neat. I ended up getting into spectroscopy, especially with the guidance of Fred Lossing, who some of you may know the name from Fred Lossing Observatory. He was also a very prominent member of the Ottawa Centre for several decades. And you have different prisms. This a little closer. This is you end up opening the camera by literally opening the door. You didn't have if you tried to pull the light block in front of the photographic plate or film, that would move things. So you didn't want to. So you'd pull the plate, hold the shield in the plate holder, and then you carefully open the end of the telescope. On the left-hand side, you see some plates that Doug O'Brien end up taking, and you can see a number of the artifacts that you get if you're not careful. If you take a long if you're looking at you've got on the top, you've got two relatively thin lines, and that's actually the spectra of some stars. The one that's in the middle, it's a much brighter star, so you have halation around it, and that reduces the contrast of the spectrum. You really don't want that. So you have to judge your exposure based upon how bright the star is that you want to measure. Another aspect of it is that you're using the star as the slit of the spectroscope. So you want the star to be very focused to be able to resolve the fine spectral lines in the star. However, if it's a very well-focused star, you end up with a dotted line, and that's very difficult to read the spectrum on. So you have to drift the telescope at right ascension to spread that line to make more of a ribbon spectrum rather than a line spectrum. And of course, when doing that, you end up reducing the brightness of the object, so you're taking longer and longer exposures. With the 15-inch prism, then you had a large dispersion, and that just spread the light even more. You could only really use that on very bright stars. And for the smaller prism, you could then make use of it, take spectrum of somewhat fainter stars. The setting circles are something that I guess most people these days don't use anymore, at least not with modern telescopes that have digital readout. But this is a picture of the right ascension circle, or actually it's an hour angle circle on the astrograph. So you've got the right ascension that will give you essentially the longitude of the sky, or be able to calculate the right ascension of the object. And then you have a declination circle that gives you essentially the same as latitude, but in the celestial sphere. Now, you have to aim the telescope very carefully, because in those days, remember, you didn't have very detailed star catalogs or atlases. So you had to aim the telescope to put whatever your target was in the middle of the frame, or at least frame it the way you want it. But you can't look through the telescope. So you have to do this by dialing in the telescope, pointing at a particular place on the celestial sphere, and the stars will be where you expect them to be. To do that, you have to measure things very, very carefully and aim the telescope very carefully. So on this particular slide, you see the main hour angle, very large white indications. Then on the side, you have some other rather complex thing, and we'll talk about that in a few minutes. The main drive comes up is mounted inside the pier, and the main drive shaft comes up out of the pier to a miter gear that then turns the worm gear that then turns the worm that then turns the worm gear. We don't see the worm gear here, and that's because it's covered by a strap to keep the dirt out, because a bit of dirt, a dead bug, would cause the telescope to not travel at the sidereal rate. The setting circles are kind of neat, I think, because if you look, for some of you that saw the telescope when it's set up at the museum, you recognize the large white numbers on the dark rings. But what you don't see unless you get really, really close is that there's another ring associated with that. And in the lower right-hand corner, you can see a zoomed in version of it. The dark area is actually the dark rim with the white letters, but beside that or parallel to it is a very finely divided etched scale that gives you a much higher resolution, much more accuracy in aiming the telescope. But you can do better with verniers. So on the lower left-hand corner, you can see an example of vernier for those that aren't familiar with it. We have from 20 degrees to 30 degrees, scaled off every degree or so, which is roughly what it's like for the declination circle. And then the engraved portion, which is marked off here as gray, you have much more finely divided, maybe down to in the order of maybe half a degree. Still, that's not very accurate. So you end up having a vernier scale, which is attached to that complex mechanical assembly, and for that you have gradations of the same number of gradations, but now you shrink that by about 10%. So now on the right-hand side, you end up seeing that. Let's go on the left-hand side. You see, the right-hand side one under by the 20-degree mark. You can see that you can estimate the position to be about 21 and maybe 21.2 degrees declination. Well, by using the vernier scale, you look over to the right until you see the lines line up with the etched marks on that disc. And actually, you can interpolate it there to see it's not 21.2 degrees, it's actually 21.15 degrees. So you get much higher precision in aiming the telescope, which means you're much more assured of where you're pointing the telescope and that your target star will be on the photographic plate. Now, to be able to do this at 3 in the morning is not pleasant. You need a lamp to illuminate the finely graduated scale and a magnifying glass as well to be able to look into it. Now, remember, this is standing about 6 feet above your head, and so you need a step ladder to get up and contort yourself to be able to see this stuff. But it does works very, very well. This is an example of the drive mechanism. Now, the one on the right-hand side is the drive cavity or the drive bay for the 15-inch Brashear telescope. And we have on the left-hand side the governor mechanism. And the governor mechanism works by the telescope essentially almost literally runs open loop at a speed. But if it goes a little bit too fast, then those weights flail out a little bit further, increasing the inertia, and that slows down the drive. If the drive slows down too much, then the weights come closer to the axis and the drive speeds up again. This means it's never really moving at exactly the right speed, and hence the reason for you to guide. Now, this is another interesting, because you have to guide, you have to somehow find a guide star. Well, you don't want, one of the problems with having a separate guide telescope on a telescope is that, and we had this with the 16-inch telescope that was at Indian River Observatory, is that the guide scope can droop with respect to the main instrument. And that ain't going to happen with the astrograph. The entire system is a huge metal casting, and the guide telescope, which is the one in the center of the field here, is encapsulated or held in place, grabbed and clamped by a rather large clamping mechanism. Well, if you're going to try to find a guide star, you have to relax that clamping mechanism so you can move the guide scope around. And there's a bit of a ball and socket that allows you to move the guide scope around, similar to, again, the design that was on the 16-inch telescope at the Fred Lossing Observatory. You had guide crosshairs. However, the guide crosshairs weren't etched in glass. They were literally spider webs. The radial threads in the spider web don't have the stickiness on them, so you take those out and then you stretch them across the eyepiece in the right place. And over time, the those guide hairs would eventually break or bend or get dirty, whatever, and they had to be replaced. So you have to find a spider web somewhere and replace them. I never had to do that, but that's what I'm told. So the axis you have on the top, we have the finder telescope. So you get in the general, two ways you can name the telescope. One is to dial in the approximate hour angle of the part of the sky you want, swing the dome around so that you could, so the telescope's looking out through the slit, and then you zero in on that position using the setting circles. Another way is to use the finder telescope, which means you just move the telescope around so it's pointing in the part of the sky you want, and then you start refining the position from there. However, if you look at this picture, the finder telescope is at the top of the instrument. So you're looking up, you have to climb up about 8 feet to get to it. And that's not going to happen. However, it's there. Zooming in on the end of the guide scope, you can start seeing the clamps that's required. So it's not just a matter of clamping it with a nut, clamping a nut down or clamping a bolt down. There's a bunch of them. So that makes it, I never used it. I kept my exposures relatively short. But what is also kind of neat is that you're pushing this thing, and this thing weighs, I don't know, maybe 50 pounds or more than that, maybe 100 pounds, because it's made out of metal. So you can't get it exactly on your guide star. So what you do is you move the eyepiece back and forth and rotate the eyepiece until the guide star is on the guide hairs. So it's a very hands-on process. And you've got illumination over here to the side, a small electric bulb to illuminate the guide hairs. And at f12, that's pretty long. You're not going to be seeing many faint things. However, stars are very tolerant of light pollution and also the focal ratio. So although you won't see any nebula in the guide telescope, you don't really care. You're just looking at the stars. So first of all, before you take a telescope, you better start lifting weights, taking pictures of the sky. You have to crank open the dome. And so there's a large pulley and you start hauling down. You can almost call it a halyard that raises up the mainsails in a boat. You rotate that, you pull down on that, and that opens the door, opens a slit on the door. And this is a very heavy dome, and it'll also rotate the dome. Then you got to find the target with the setting circles. There's a trick to that, sadly. Find the guide star in the finder, and then in the larger guide scope, because the finder shows you a much wider field of view. That might help you zero in on an acceptable guide star. Then you've done most of the heavy duty work, so then you put your parka on and so on, because you're going to be motionless for about the next hour, and it's -20 outside. You then have to focus the camera. How the heck do you do that? Well, you use a magnifying glass on a false plate that's in a plate holder that's in the same position of the same telescope that you want to use. Then you adjust the focus by looking at the star's image on that plate. So that being done, then you in the dark room, you load the plate into the plate holder, bring it up, you mount the plate holder into the telescope, back into the telescope. And oops, you got to get the telescope to drive. So you better make sure that the heavy weight that provides the energy to drive the telescope is at its top dead center. And it'll work for an hour or so before it's gone all the way down to the bottom dead center, then the telescope stops. So you're kind of limiting the exposure length that you can use. In the 15-inch, I think it was about an hour, hour and a half before you had to wind up the weight again. And then you pull the plate holder screen and open the shutter on the top of the telescope, and you're off and running. Guess we'll.
Okay. So what happened was in the 1960s, the Dominion Observatory was an active research observatory, but it wasn't doing the same research as it was doing back in the early days. By then, what they were doing was doing work on establishing things like continental drift, and they had other instruments. So this small dome photoequatorial telescope was no longer being used by the observatory. Permission was granted to some observers from the RASC to use this scope. And so we sort of jumped at it because what it did was it gave us access to professional equipment. And I joined the RASC in 1963 and Rob in 1969. Then a group of us, under the guidance of Fred Lossing from National Research Council, we refurbished the scope, rewired it, added electric controls so that we could advance and retard the right ascension without having to turn those awkward knobs and, of course, jiggle the telescope as we did, and basically cleaned everything up. So this is an article from the Ottawa Citizen at the time showing some of us. There were sort of a group of 7 of us at that time, and I'm the guy in the lower right of the picture. So that's the small dome photoequatorial building, and it was primarily a camera, as we said, and that's what it was built as, and that's what we tried to use it for. We tried to use every capability, but we had access to professional equipment, which was quite rare because back in those days, amateur astronomers had to make their own telescope, grind their own mirrors, etc. And yeah, I had my 4-inch telescope that I had built out of pipes and things like that, but this was real quality professional equipment. So I did this study on star brightness using the mechanism that had been established back, I think it was Yerkes Observatory in 1912, started using that photodensitometer approach. I used that same approach, and I won the Ottawa Science Fair. And then the year after, I built a radio telescope and won the National Science Fair. Rick Salmon, one of the other people that you'll see in that photograph, he built a solar spectroheliograph, and he also won the Science Fair. Les McDonald, one of the other people in our group, built a meteor camera. Rob Dick and several others, and you'll see at least one other in the picture, they concentrated on the astrophotography. You want to get into this, Rob, or do you want me? Okay. Stay close.
Yeah, this is this you probably have never seen that. Well, some of you probably have never seen this. Some of you have. The gray hair certainly have seen film, but this is sheet film. And if you go back a little bit earlier, it's you got film on plates, and the film on plates, don't drop them because they cost. Well, it would cost me probably about 4 or 5 months allowance to pay for one plate. Fortunately, there are a lot of plates and film left over from the professional work that we're able to still make use of these. So we got a very good deal on that, but we're still very careful with the film and plates. Originally, you had 8-inch by 10-inch plates. They came in boxes. And then we have 4- and 5-inch high plates as well for when you didn't want to record that large an area. We had plate holders to accommodate both these sizes. And then later, 4-inch by 5-inch film was substituted simply because they're a lot cheaper. And the example here is this Ilford film that Doug has. The film speed was very slow by the standards of the 1980s, easily. The plates, for example, were the ones I used were 103 AF, which had an ISO or ASA in those days of roughly 50. And then as time went on, the Ilford film got more and more sensitive, but still it's in the order of 100 to 400. And compare that with some digital cameras where it's in the tens of thousands. You had to do your own developing. The chemicals had to be mixed and a uniform and constant temperature. So that's something you did when you showed up. The dark room was heated, so it could be kept at the same temperature. We use typically D19, which is a relatively fine grain but high contrast developer in those days. Then you had to have something a tray to wash the developer off when the time ended for the development, and then you put it in a fixer that removed the unexposed chemicals in the film, in the emulsion. Now, because the film itself is panchromatic, the 103 AF were sensitive to roughly the green to the far red, so you couldn't have any light in the darkroom. When you're opening the boxes, or when you're loading the plate holders or the film holders, to when you're developing. So everything had to be done by touch. And that was, it was a challenge, but it became part of what you end up doing. And when you make a print, for example, you can use a red light in a dark room, but you had to do it in complete darkness. The dark room, fortunately, was in the building. It was on the first floor, and then you had the observing deck on the second floor. Here's an example of some ways that Ilford, for example, marked the film so you could tell which side the emulsion was on. And you had the serrations on the edge or one corner of the film. And then you just learned that when it's in the upper right-hand corner or upper left-hand corner, the emulsion was on one side or the other. And you just made sure that you remembered that, because you have to have the emulsion pointing up the telescope towards the objective lens. Another way of doing it was that I did with using the plates, was that you couldn't notch those plates. They were quite brittle. So you end up to wet your finger, and you could rub your finger on the edge, just on the corner of the plate, and the emulsion was slippery, the glass was not. So that allowed you to determine which side was which when you pull out of the box. Now, in a box, they're all on the same side, but at 3 a.m., you're not thinking too straight, so it's good to check it anyway. Here's an example of Doug took, and it's an example of what happens if you have a moment lapse in concentration. Now, your brain usually recycles or resets about every few seconds when it comes to concentration. But at 3 a.m., I'm sure it's much longer than that. So here we have an image, but you can see slight trailing in the stars. Now, you don't know about this until after you develop the plate. So you just spend maybe an hour getting the telescope ready, you develop the film, 30 minutes plus, and then you find out, oops, I made a mistake. You have to do it all over again. And that's after you just spent a few months of allowance worth of plates, with that one plate costing so much money. So you had tracking errors with the backlash in the drive and the inaccuracy and just the machining of the drive. You literally had to stay on top to make sure you're tracking the images properly. So, and you tend to have long exposures because the film was so slow. Now this comes up with another aspect of it, and that is hypersensitizing the film. Because there's a problem with film that you don't experience with digital symmetry, digital imagery, and that is something called reciprocity, where if you double the exposure, the density of a star, for example, star's image on a film will double. If you half the exposure, then the density is going to be half. Well, with low intensity illumination, you have reciprocity failure, and it doesn't do that anymore. Rather, the film might start out at being ISO 400, but at the end of about maybe 2 minutes, it's now down to 125. And that's a relatively short exposure. This is a test I did with between Kodak Plus X, which had an ISO or ASA of 125, and Plus X, which had a ASA of 400. They were about the same after 2 minutes. And yet the Plus X gave you much finer grain. So hypersensitizing became very important because the film that you're using, you didn't want to spend hours and hours guiding this telescope, especially when you found that the drive wouldn't run that long. So we have to come up with the hypersensitizing, which I'll describe in a few minutes. This is an example of developing the plate. You mix new chemicals, set the temperature roughly 22 centigrade or so. And in full darkness, you remove the plates from the film holders, submerge them in the developer tanks, making sure you feel around and you put them in the right tray, developing tray. Then you fumble around for a timer and you turn on the timer because all this time it has to be complete darkness. Then you sit around waiting for the timer to time out. As I mentioned, the dark room was on the ground floor. On the second floor, to get to the second floor, you walk up a spiral staircase to the observing deck, and here we have Rick Salmon coming up through onto the deck, the observing deck, and you really had to close those hatches before you turn the lights down. Okay. Reciprocity failure is a phenomena that when I was doing this was very vaguely understood, but it seemed to have been at the time, and I really haven't looked into modern theories about it, but was either oxygen or moisture in the film. With the very faint light that hit the film would cause the breakdown of the chemicals in the silver halides, but over time, but it was such a weak light, the minerals didn't drift apart very far in the emulsion. The emulsion was gelatinous and it would prevent the motion of them. And so over time, they would slowly come back together again. And that was really bad. So one way to do it was to change the emulsion a little bit by getting rid of the moisture, getting rid of the oxygen. And you did this by, one way that Doug did was to soak the plate in ammonia. And that worked. Another way of doing it is to soak the film in pressurized hydrogen, which I used. I didn't do it, but a friend of mine did that. Another way of doing it is to cool the emulsion with dry ice. And I made a dry ice camera, cold camera for that. And all those worked very, very well for a period of time. And here's an example of it. Hypersensitizing greatly reduced the degradation of the speed. So it didn't increase the speed. You still were limited to ISO or ASA 50 or ASA 100, but at least it stayed at that speed for the length of your exposure. And that allowed you to take an exposure of 10 minutes that would otherwise you'd have to be sitting there for literally an hour or 2 hours. Focusing. You would use an eyepiece to inspect the focal plane. However, over time, temperature changes, and most of you know what happens when the temperature of your telescope changes and how the focus changes. So when you do a focus at the beginning of the exposure, because you're not using the film, the photographic plate or the film, you focus the telescope, take out this focusing frame, put your film in or put your plate holder in, and then you start your exposure, and you can't touch it after that. There's no correction. So what could possibly go wrong with this whole process? Well, focus changes over time because the temperature falls over time. So if you took a short exposure right after you focused the telescope, it was pretty good. If you tried to do it, then redo it, take another image, say at midnight, it would be out of focus. So you have to refocus between each plate. And if you take a long exposure, even the first plate will be out of focus because the focus shifts. And hence that's because of the temperature. Also, the hypersensitization was temperature sensitive. So if it was a warm night, it didn't last as long as it would on a cold night. The other side, what could go wrong? You're trying to manually move around a half-ton telescope. This telescope, fortunately, is designed not to move, which means if you climb up through the staircase and you hit your head, you got a big dent in your skull and the telescope will hardly know it happened. So it's not a pleasant thing to do. Same thing happens at the telescope in Victoria. You have very slow results. You don't know something went wrong till after you've gone to all the trouble of taking the exposure, developing the film, letting the film dry a bit so that you can then inspect it with a magnifying glass. And that takes perhaps 2 hours to do all that after setting up, and then you got to do it all over again. And here's some examples I think Doug will talk about, or do you want me to? I guess I can mention. And you can see that the quality, or I shouldn't say the quality, but the character of the images. On the left-hand side, you can see a mottling across the frame. And some of this could have been done to when you put the plate into the developer, you have to keep moving the tray of the developer to make sure the developer moves around the plate uniformly to make sure that it develops the entire surface of the plate the same way. If you don't do that, then you'll end up getting mottling in the emulsion. Also, this is a plate and it's been around for how many decades?
59 years.
Almost 6 decades, and things happen to film over time. And what used to be a really nice image turns out being not so good after that period of time. The middle plate shows that that emulsion is very, very sensitive and it's easily damaged. So you have to be very careful with it. Even when you're being careful with it, things happen. A piece of dust gets in and then it moves around, the plate moves around inside the envelope and you'll end up scratching. The one in the upper right-hand corner is much more, is a nice looking plate because it's uniform. However, where are you looking in the sky? Over time, unless you take really good records, you have no idea what this is. So you have to take very good records, and not just the records, but you have to document the plate physically so that you don't forget what target you're photographing. The other aspect of photography at the Dominion Observatory is shown by this slide. And that is we're about, I think it was a couple of 100 meters from several very bright unshielded greenhouses. So as a result of that, yeah, there's much less light pollution in the late 60s. The suburbs lacked street lights. However, there are nearby greenhouses and Carling Avenue is 100 meters away. And also in those days, streetlights didn't have shields. Also, for a guy like me who was in high school, there's no bus service after midnight. So if you stayed up to past 10 or 11 o'clock, you're there for the duration until the buses start in the morning. And unless you had a supportive father, or you're lucky enough to have your own driver's license and had the access to your parents' car. And I'll pass it back to Doug.
Okay, we're running a little over time, so I'll try and be brief on this and basically say that while doing modern digital photography is much, much better because you can stack, because you can do things that we couldn't back then. Photography on film was a one-at-a-time shot with a lot of effort to take a single shot. And everything was monochrome and everything was, well, the contrast was not nearly as good. And working in the darkroom was difficult, but that's the way it was back then. The Brashear Doublet Telescope is now on display in the Canada Science and Technology Museum in Ottawa, Ingenium, one of the 3 museums that are under Ingenium. This is one of the other ones. So go visit it. we want to learn from this past experience. So we're quite willing to answer questions, but I think we'll have not much time left because we're a little over. And the other thing is that, in our opinion, the Dominion Observatory should become a museum of astronomy and geophysics. We didn't even get into the geophysics part of all of this. Teaching the public and respecting Canada's major contribution to timekeeping, space, and earth sciences. Thank you. It's fully cited if you want to go through any of the sources, but that'll be later to look in detail.
Thanks, Doug.
Okay.
Yeah, we are running a little short, but are there any questions up at the top?
Okay, we have one question online from Jean-Sébastien Godet. The 15-inch telescope, when it moved from the Dominion Observatory to the Science Museum, was primarily used for outreach until the renovation came in. It's now in storage. Are there any plans to reuse that telescope?
No plans at the moment, as far as we know. It's sitting in storage. It's well stored. I mean, it's a very good storage facility, so there's no damage to the equipment. But in order to do any of this stuff, you need funding. And in order to build a public observatory, you need sponsors. So any of you got a company that's willing to sponsor development of a public museum, please volunteer. The point is that we need to have sponsoring for the development of such a museum. And the museum, I say, of astronomy and geophysics, because this is also there's also at the observatory the reference gravity point for Canada. There are a whole lot of other things. The seismological vaults I didn't get into. So such a museum would be very beneficial, but we need somebody to sponsor it.
Thank you. The others? No? Okay. All right. Well, thank you so much, guys. That was very detailed and informative. All right. All right, just a quick run through. I'm going to speed through this. Benefits of our membership is first and foremost is the members in our club there that are knowledgeable and friendly and we're very willing to share their knowledge and pick your brains for yours. So super benefit of our club there. On the hardware side, we have the Ted Bean Loan Library, where we can actually lend out telescopes if you haven't got one but are considering buying one. You know what they say, try before you buy, and it can save you some grief. We also have actually, yeah, we have our loan library. There's a slide there with Estelle. Is Estelle here tonight? Oh, hi, Estelle. She's our librarian, and she can help you out. We've got quite an extensive library that you can peruse and borrow books from. Okay, membership goodies. Along with your membership, you get the Observer's Handbook, a very reputable, notable journal that's been a reference book that's been around for decades and is, I still love using it out in the field. You also get access to the journal and our monthly astronotes. All right. The members also get access to the Discord server where you can share ideas with fellow members of the club on that. It is our own Discord server. You get a subscription to Astrophotic Pro at a club discount, 66 a year. Is that right? Have I got that right? It's yeah, just. Oh, right. Yes, if you're not a member, the pro version is $66 a year. A wonderful program for a wealth of data, especially on conditions for observing, like seeing and cloud cover and such. And we will rock through that. Our membership fees are $113 for an adult membership, $107 for a family membership, plus $15 per adult and $9 per youth. And we also have a youth membership for those under 21 years old or under 25 if you are a student. All right, enough of me yakking. We will introduce Adam Brown, and he's going to talk to us about stellar streams in the galactic halo. Are you here, Adam? Hello? Oh, I thought Adam was going to be presenting live, actually. Anything online there, Chris? No? Ooh, okay. I think we just saved some time. Um, okay. Is he? Okay. No problem.
Hi. Do you hear me okay now?
We've got you.
Okay, I'm coming through? That's great. Yeah, so I want to present on stellar streams, which is a class of astronomical object that I only recently learned about. I think it's really cool. And also it's only fairly recently been discovered, since kind of going back to the 70s, but really in earnest since like 2000. And yeah, I really enjoyed the previous presentation on the Dominion Observatory, and it's like an amazing, I think it's an interesting contrast, the kind of cutting edge astronomical techniques 60 years ago and what's available to amateurs today. Can we go to the next slide? Oh yeah, and I'll just say real briefly, my outline, my talk is, what are stellar streams? I'll present a kind of an observation of a prominent stellar stream, and you might find I'm like stretching the definition of the word observation there, but that's how I think of it. But it's fundamentally just a data analysis done with the computer and with the publicly available databases. And then I'll just mention some of the interesting implications of stellar streams for galactic astronomy and actually for cosmology. Yes, so kind of like to contextualize what I'm talking about and what I'm referring to as an observation, this is for Milky Way astronomy, people call this the Gaia era. This is the Gaia spacecraft operated by the ESA, or was operated by the ESA. I'm sure most people have heard of it. It spent several years orbiting at Earth Moon Lagrange 2 and doing this like incredibly precise astrometry of Milky Way stars and measuring positions, also proper motion and parallax with like totally unprecedented precision. I think expanding the number of stars for which like reasonably accurate parallax measurements are available into the hundreds of millions, orders of magnitude beyond what was available before. And yes, so this is one of a number of survey projects over the last 20 years. I think of Slow Digital Sky Survey, All Sky, which was an all sky spectrographic survey. There's Pan-STARRS photometric survey, on and on. There's the Vera Rubin Observatory, which has just opened up, and there are all these programs of essentially like whole sky observation, collecting data on millions or billions of objects, putting it all in a database and making it available for, what's cool is it's also the open access era. And as amateurs, we have access literally to like the same instrumentation and data sets that professional astronomers are using. And Gaia's been, there's, I don't know how many thousands and thousands of papers have been published on discoveries made just by, processing the information in the Gaia data set. Yes, we could go to the next slide. Stellar streams are, essentially TLDR, they're tidally disrupted globular clusters. So, a globular cluster is a very old population of stars that are orbiting the galaxy, often like, at a distance outside the galactic disk. They're often on like highly eccentric orbit, so they might pass through like or near to the galactic bulge, or they might pass by like a dwarf galaxy at some point over those billions of years, and their gravitational cohesion can be disrupted into essentially like a stream of stars. It's tidal disruption. And so in the last 25 odd years, since 2000, about 150 of these stellar streams have been discovered, which are, essentially thought to be disrupted globular clusters. Some of them can be connected to existing globular clusters. Some of them, there's like no known progenitor. They're potentially just like completely disrupted. In the next slide, I'll just kind of do just like a quick, couple looks at the kind of like structure of the galaxy. On the next slide, there's, simplified structure of the galaxy. There's a bulge, a couple kiloparsecs in radius, like 6,000 light years in radius. There's a thin disk, which is 20 kiloparsecs radius, like 60,000 light years radius. There's our sun kind of like at a nondescript position of the disk. And on the next slide is, you can see there's also a large, what's called a stellar halo surrounding the galaxy. And that's like a volume in which like it's very sparse compared to the disk. The bulge is quite dense. Disk is still fairly dense, and then the stellar halo is quite sparse. But you find stars and the Magellanic clouds would show on this scale. I didn't plot them into the map, but there's some dwarf galaxies and stuff. On the next slide. This is my personal favorite object to look at through the 18-inch telescope at Flow. I just don't get sick of it. M13 is, there's an interesting connection actually between M13 and the specific stream that I want to highlight with my talk tonight. M13 is, and I think like fairly typically of a globular cluster, it's very old. It's 11.5 billion years old, roughly. So quite a bit older than the Milky Way itself. And, I think, a pretty substantial fraction of the age of the universe. It's like, this is like a really early, these are really early stars, and they have very low metallicity, meaning that they have a much lower proportion of heavy elements heavier than hydrogen and helium. they have a much smaller proportion of those heavy elements than the stars in our stellar neighborhood do, stars like the sun or stars in the galactic disk. And it's also way out above the plane of the galactic disk. And in the next slide is I've plotted some of the kind of best characterized globular clusters on that map of the galaxy. So there is a like concentration towards the bulge, but also they're spread all through that stellar halo above and below the disk. And there's no, I don't think there's any like preference for the plane of the disk. I kind of think of them as comets, like kind of an Oort cloud of the galaxy, because they're out there in random directions, not aligned with the plane of the galaxy, and they come in often on these like highly elliptical orbits, scoot by the bulge, scoot through the galactic disk, and then back out into the stellar halo. On the next slide is a plot of the known stellar streams. And actually, the next slide again is just the same plot, but at a little further distance. And yeah, that's the same kind of ideas. The globular clusters, they're out in the halo, but they also scoop through the disk. Actually, if we go back to the previous slide, so these are streams. These lines are streams of stars. They were initially all packed together, but they've in a globular cluster, but they've been like stretched out. I kind of imagine the globular cluster like moving through its orbit, and stars being like basically like dynamically ejected from the cluster because of interaction. So it's kind of like, I imagine it's sort of like spitting stars out behind it. So they're all co-moving in a line. And essentially what they're doing is they're tracing out an orbit around the galaxy. So all these stars are on the same orbit. They're just at different positions of the orbit. And something just like by looking at this plot, you could see something interesting is that the orbits look crazy. They're, some of them are like, they're like these wiggly lines. Some of them are big arcs, but some of them are these wiggly lines. And, that's in my understanding and my interpretation is that's like an interesting witness to the fact that galactic orbits are a lot different than, say, a solar system orbit, where, solar system basically effectively like all the mass is concentrated at the center in a point. And so the orbits are these like super smooth ellipses, with like occasional, some minor perturbations, of the multi-body interactions between the planets. But in the galaxy, the mass is like spread out all over. There's the bulge, which is kind of like the sun. It's a central concentration of mass. But then there's also the disk, which isn't uniform in 3 dimensions. It's like it has a plane. So it's going to attract stuff. Stuff's going to be attracted down into the plane preferentially, not just like inward towards the bulge. And then there's also the dark matter halo, which is, I'll come back to actually. So you can see that that galactic orbits are not just these clean ellipses, but they're actually like quite complicated paths. So if we go forward to the next slide and then the next again, I'll talk a little bit about the observation that I want to present. So I was following a tutorial with all of this. It's astronomical data in Python put on the web by a guy named Alan Downey. And it's really excellent. It's a tutorial on doing astronomical data, querying data sources like Gaia, processing and analyzing and all this stuff, creating figures. It's really, I really learned a lot with it. And I'll show in the subsequent slides, I'll show kind of what the process that I went through with this. The next slide is just a screenshot of my Python environment. So this is just to like introduce kind of the tool. This is, you could think of this as like instrumentation, basically. It's the Python programming language. It's the Jupyter notebook is a kind of like environment for programming, and you can kind of like program in little chunks, and then you can generate graphs and tables and look at the tables and stuff. So it's just a good tool for doing this kind of data programming and data analysis. And then the last little bit on the bottom of the screen there is a bit of ADQL, which is the Astronomical Data Query Language, which is a standard for accessing information from these big astronomical data sources like Gaia and SDSS, etc. It's basically SQL if you've done any database programming. In the next slide, yeah, okay. So I'll try to, I'll just to keep it simple. What the process was, okay, first, and I'm working, this isn't like a process of discovering a stellar stream. This is, there's a stellar stream, GD1. I know where it is in the sky. I know how far it is. I know kind of like the characteristics of its population. So I'm just like trying to see if I can find it in the data. And this is essentially like how, I'll say this isn't something you can look at through a telescope, because like in this image here, this is a plot of the stars that Gaia has found in the location. This is like a 120-degree arc of sky, about 10 degrees wide. And this is actually just a sample of like, I think like 1% of the stars that Gaia has found at that location. And the foreground stars are like 4 orders of magnitude more numerous than the stars we're actually looking for. So yeah, it's not like observable like visually. So what we need to do in order to observe it in the data is to like filter this population of stars, and then the stellar stream will kind of like pop out. And I'll also mention just real quick, this is plotted in a special coordinate frame, which is just basically like 0 is the path of GD1 in the sky, and that just makes it easy to reference it instead of instead of working in like a curvy RA deck equatorial, instead of the path curves through the equatorial coordinate system. So this just makes it a little easier to work with. So in the next slide is a plot of the candidate stars in proper motion space. So basically each point represents a star, and its position in the plot is a reflection of its observed proper motion. So the thinking is, for the stellar stream, the 0, again, the 0 of our coordinate system is the path of the stellar stream. So the stars are all moving along that path, so they should have a proper motion of about 0 perpendicular to the stream. And they should all have about the same proper motion parallel to the stream because they're co-moving. And so looking at this image, there's like a big blob on the right, but there's also a faint blob on the left. On the next slide, I selected this kind of faint blob on the left, which is that's like the stars of the stellar stream. There's a kind of like called an overdensity in the proper motion space. Yeah, so on the next slide is, and this is just translating that back to the equatorial frame. It won't really get into that. Yeah, on the next slide, so these are just the stars that are in that boxed section, on the proper motion graph. So they're just the stars that have roughly, they all kind of have roughly the same proper motion. They're not deviating from the stream center line, and they're all kind of moving together. And you can just faintly see a hint of the stream emerging from that star field now that we've discarded the ones with the kind of all the other random proper motions. So the next step is to create a filter of the stellar characteristics. So this is the famous color magnitude diagram, the Hertzsprung-Russell diagram, basically, which many people may be familiar with. It's a plot of the brightness of a star, for a population of stars, a plot of the brightness versus the color. And what you find is there's a kind of characteristic path that stars are found on in that plot. Basically, as stars become more massive, if you take a low mass star, it's fairly cool, dim and red, and a more massive star is more blue and brighter, and so on up the line. And so for a population of stars in a color magnitude diagram, you can kind of see a characteristic like swoop from the lower right to the upper left. And actually in this diagram, as I see it, in this plot, I can see kind of two sequences. I see like a brighter one, sort of both at the lower right of the plot. I see like a bright, thick bar going from like color 1 to like magnitude 18, 17, and then a dimmer one below it to the left of that. And so the thing is, obviously for a population of stars, the position of the main sequence on the color magnitude diagram, it's going to be influenced by the distance to that population of stars. So if they're closer, the whole main sequence is going to move up the diagram because it's going to be brighter. And if they're further away, it's going to move down the diagram because they'll be dimmer. But the overall shape of the main sequence will stay the same. And then the other thing that's very helpful is different metallicities, different stellar compositions have different positions on the color magnitude diagram. And a lower metallicity stellar population, like, for example, M13, is going to be a little bluer than a like population 3 galactic disk set of stars on the color magnitude diagram. So on the next slide, actually we'll just skip this one. Don't need to get into the details on that. But this one is what's called an isochrone for an M13 like population. And I just you can get this from like a little web form. You put in what's the age, what's the metallicity, what's the distance, and it will spit out it'll spit out a little curve like this. And it shows you where stars of that type should appear on a color magnitude diagram. And we can see that it lines up really nicely with that kind of smaller left-hand main sequence of stars. And on the next slide, I basically just selected the stars in and around the main sequence for that isochron. And I skipped the part where the curve kind of comes back over near the top because it's getting mixed up with other stellar populations there. And then in the next slide, we replot just so this is the stars that were first, they were selected for the proper motion, and then they were selected based on their color and magnitude to be in just that specific color magnitude region, which is, stars like the stars in M13. And yeah, the stellar stream actually shows up really clearly, which is pretty cool, which, to me, I'm like, oh, I see it. There must be something there. And yeah, so in the last slide, first this is from a paper. This was a paper that inspired the tutorial that I followed to create these previous images. And so in this plot, the authors have labeled some of the features. You could see sort of structural features of this stream. There's what they call the spur. There's kind of the stream is like bifurcated a little bit. There's a couple gaps where there's an absence of stars, and then there's places where the stars are more dense together. There's like kind of a little blob in there, which the author has labeled progenitor ? I think they're suggesting that maybe that's the originating globular cluster, although there's not nearly the evidence to say one way or the other. And so what I think is really neat about about stellar streams, is that they can, essentially they can act or could act as a probe of the overall gravitational potential of the galaxy. So again, there's all the visible matter in the galaxy, which is much denser towards the center, but is inferred or strongly implied by observations of, for example, the rotational speeds of different parts of the galaxy and of objects outside the galaxy, like dwarf galaxies and globular clusters. It's implied that there's a vast amount of, so-called dark matter. There's a vast amount of mass that's contributing to the gravitational potential that we just can't see. And so, there's a bit of, it's very mysterious. Everyone would like to know what it is. Is it kind of funny kind of particle? Is it little miniature black holes? One thing that is known about it is there's a kind of like an overall shape, which is kind of like described as like kind of a funny squished like beach ball, where it's sort of spherical, but it's like each axis has like a different kind of length. And, maybe it's due to like interactions with dwarf galaxies and other galaxies. But one prediction, and I don't understand how this works or what the basis of this is, but apparently there's a prediction that there should be a kind of structure within the halo called subhalos. For cosmological reasons, they predict these subhalo structures, and there's a kind of like characteristic size that they're predicted to have. And then the interesting thing is, if that is so, these stellar streams, which are often orbiting, like GD1 is orbiting way outside the galaxy, it's not really interacting with anything massive and dense in terms of visible matter, but it might be passing through these patches of denser dark matter concentrations. And there are predictions about what kind of effects that might have on the stellar stream. And in particular, there's predictions about the size and spacing of the gaps that might appear in stellar streams if those subhalos exist and if the stellar streams pass through them. And so this is like, active area of research. And I don't know, maybe we'll know it someday soon.
Well, thank you, Adam, for a very detailed discussion of the halos. I wasn't aware that you could get access to that detail of data from the Gaia, so that's pretty cool. I'm going to have to forego questions, unfortunately, because we are running a little bit behind. Sorry about that. And thank you again. All right, we're going to move on to our observation segment. And again, I ask the presenters to be really brief with your stuff there because we are pushing the clock here a bit. So first up, Mr. Olson. There you go. Yep.
Okay, I'll keep the button moving. This is one of Richard's challenge objects. This asteroid is a large object in the asteroid belt and is large enough to be classified as a dwarf planet. It is water-rich world. It is visited by NASA's Dawn spacecraft. The Roman god Ceres is known for her role in fertility and harvests, with the word cereal derived from her name. This is obvious, but it never occurred to me. Okay, now, which one is it? There it is right there. And then a couple of days later, I took this picture of it just to show that it moved. And how can I be sure I was on Ceres? Well, I used a computer to point my telescope. So what can I say? Okay, what's going on? That's all just my screen, okay. I noticed that Eros was in the area. And again, my computer pointed right to it. The little dash in the middle is Eris. So I snapped a couple of pictures of it just as same time as I was doing Cirrus. And again, I imaged it over 2 days. And so it went down to the bottom left-hand corner there. It's a small peanut-shaped asteroid, about 30 kilometers long, very small compared to the other one. It's visited by the spacecraft Shoemaker in 2001, which landed on the asteroid. It has an orbit around the sun similar to that of Earth. 1 year on Eros takes only 1.7 years. Another challenge object, M15, a very old and dense globular, as we just heard, located in the constellation Pegasus. It's about 30,000 light years from Earth. It's a wonderful sight in almost any telescope. Get out and look at it. This galaxy contains many star-forming H2 regions, quite similar to M33. It's about 8 million light years distant. Sorry. Another challenge object. This galaxy is about 150 million light years distance. It has a ton of starburst activity, with many of the stars being formed in the past 100 million years, which sounds like a long time, but astronomically not. This makes it a very bright imaging target. And then this galaxy is very similar to our own Milky Way, both in structure and size. It is not too far away, at about 40 million light years distant. It makes a very attractive imaging target, and I've imaged it several times before. I noticed in my planetarium program that it was in good location to image this past month, so I pointed my telescope toward it. I also noticed that Stephan's quintet was very close, so maybe in the same field, which it was, thus tonight's image. I do find pictures like this a little lopsided. I'm not a big fan of this. And I can use a computer program to get rid of the stars. And boy, there are a ton of galaxies in that image. Oh, you're kidding. It's right there. I see it now. Okay. M33. A little less than 3 million light years away, so it's pretty close. You will notice that it fills my field of view. It's also pretty large in the eyepiece. It is not a high contrast target, more of a big blur. It makes a really boring object to see in a telescope. The red areas are areas of star formation. I've imaged this object several times before in the past. This image is a combination of 32 hours of exposure taken over 19 different nights over 3 years. Yeah. And finally, another interesting galaxy that was another of the challenge objects. This galaxy itself is quite interesting, but I am fascinated by the surrounding nebula. I say surrounding incorrectly. The galaxy is about 60 million light years distance, but it is the surrounding nebula is in our own galaxy and is Milky Way dust. Almost has a spooky look to it. Thank you.
Thanks, Bob. All right, Rick, there you are.
So what a month we've had. When I was a young lad, say 40 years old, 45 years old, and I used to look through my telescope, look through a telescope. We had to look through an eyepiece, bare feet in the snow, and I rarely got 2 nights observing in a row. Later, I built an observatory in the backyard. I would fairly regularly get 2 nights in a row. Occasionally, wow, I'd get 3 nights in a row. Since I've retired, moved out to the lake, I quite regularly get 7 nights in a row. I occasionally get 9. In September, I got 22. I have been trying, over the past few years, I've been trying. First, I tried to reach 150 observing nights in the year. Then I thought, and I did that, and I thought, I'll get 156. That'll be 3 nights per week. So I did that. Last night was my 154th observing session this year. So I'm well on track to get better than every second night. So what have I actually got to show for it? The Kingston Center, I'm also a member of the Kingston Center, possibly, Chris tells me. They have a ZWOC Star 50 in their loan library. And so they loan it out for a month at a time to various members. I'm on an AAVS, American Association of Variable Star Observers, working group trying to see if we can use smart scopes for photometry. So I borrow it every chance I get. And when I borrow it, I also take a few pretty pictures. So this is obviously the dumbbell. I'm not going to go into a lot of detail about the objects. I'm mainly showing off some ideas of what the scope can do. M13, you can see NGC 6207. When I was young and looking through my 6-inch, I was so impressed with myself when I was able to even detect that. And now, I mean, you know, a 2-inch telescope, and it's a nice image of it. And then you can see there's even a little fainter guy here that I still haven't seen in a telescope. So that's M13. M15, challenge object. You can see the change in size. And M71, a really sparse globular cluster. It just seems to me that the C star is something that would be so easy to just go through and like take pictures of all the globulars in the northern sky, all the open clusters, and you could have you know, a really interesting study. M56, smaller still, and this is a really neglected one that kind of between Lyra and Cygnus. Some of the challenge objects, NGC 6885, quite an obvious cluster. It gets a little bit lost in the photographs, but it's nice visually. 6940. This one I was quite interested in because it's also very useful for photometric calibrations and stuff. So I can use this data for my working group as well. And 6823, oh, I should mention, I forgot with 6882 and 6885 are both in this image. And there's some confusion about what's what. You can see it looks like there's a pretty obvious little tight cluster here, but then maybe there's a bigger one here, or maybe there's these bright stars here form another cluster. So following on from Adam Brown, one of the things you can do is you can go to the Gaia data and you can actually download the data for all the stars in the area. You can find all their proper motions, and then you can actually see, is there one cluster here? Is there any cluster? This might just be a random grouping of stars. So this is something with your Python that you can do. 6823, this one, I can't remember why, but I ended up doing 2 strings of about 280 images each, and thought, well, I should overlap them because neither, this is pretty faint. This is with the light pollution filter, and it wasn't showing up great. So I stacked the 2, and so you can see, of course, they weren't aligned, so the corners are kind of wonky. But it does show up, shows up this elephant trunk here kind of nicely. So it gives you some idea of what it can do. And this is NGC 7331, and that star right there is the supernova. And I've been imaging it every night, basically, that it's been clear. And I'm going to do photometry on it, measure its brightness as it goes down. The latest thing we've been having is every 15 years, the shadows of Saturn's moon fall on its disk. We always think about the moons, the Galilean moons, casting their shadows on Jupiter. But in Saturn's case, it's been happening for the past few months. So this was back, I think, in August. And this was imaging with my 10-inch Schmid-Newtonian. And then in September, this is with the 16-inch Boltwood telescope. It's a pretty ugly image, but the shadow does show up very nicely. You'll notice also that it's further north on the disk. Unfortunately, no, this was the August one. In September, I was at Fallen Stars, the Kingston and Belleville Star Party. And so we were observing visually down in Prince Edward County. And it was a terrible night. It was windy. The seeing was really poor until about 1:45 in the morning. Suddenly, the wind died off for about 15 minutes. The seeing just locked in. And the moon was just, it was like a black ball bearing on the face of Saturn. It was absolutely stunning. And I was the only person who had stayed up late enough to see it. And there's going to be one more of these on Monday morning. Unfortunately, it's the last, and the moon shadow will actually just graze the northern limb of Saturn. And the next one is, I think, 11th of November, 2038. So that's all I have. Thank you.
Thanks, Rick. Okay, Fred Burt. Fred can't be with us tonight, but he did submit his observations. So I'm just going to read briefly from some of the notes that he provided. Basically, Fred observed a fireball on September the 21st at 4:27 in the morning, and it was quite bright. Apparently, he witnessed a fireball and its breakup over the Ottawa area. I wasn't around on that date. I was out of another part of the province there, so I don't know if anybody else got a chance to see that or hear about that, but this is the first I'd actually heard of it. So basically, you can see from his video there. Cycling through there, okay. I'm not sure. The video that I was seeing from Fred there showed a trailer. Perhaps it's in his subsequent image. At any rate, there was an explosion that he saw. He witnessed the actual explosion of the fireball. Estimated it was about 3 to 4 lunar diameters in its own extent, and it lasted. The actual flash lasted about a second. There we go. There it is on the still there. You can see the trail. Unfortunately, it was right near the roof of his house here, so it didn't capture the whole disintegration of it. He was using an all sky camera to view this. And the angle he got quite fascinated by this, and he tried to reconcile the information that he'd received about the trajectory of it with what he saw over his house, basically. And what he's looking at, I'm just going to zip through his slides there. He's down in this area of Ottawa there, and he based on again some reports that he had read, estimating where it broke up and how high it was. He was thinking that there might even be a bit of a debris field from fragments. Hard to say whether that actually happens or not, especially if depending on the type of meteor that caused the actual event. But I was thinking that there might be ground debris visible in Gatineau or even on the farmland around Barrhaven. He was actually looking to get permission to access some of the land there and sweep it with a metal detector, but I think that's a pretty long shot there, Fred. I think that's you've heard of everybody's heard of a needle in a haystack. This is magnitudes worse than that. So I wish him luck if he's going to try to do that, and if he does, I hope he comes and talk to us about it. He has requested footage from the traffic cams actually at Woodruff and Fallowfield, again just to try to hone in the trajectory vis-a-vis his location and perhaps narrow down a potential debris field. He was reading reports from other centers there. Apparently, this was actually seen at low elevation from Toronto and Sudbury. A show of hands, did anybody actually see this event at 4:27 in the morning? I thought I was a night owl. No, I don't see any hands up, but yeah, there are reports from the area there, and I believe he has. I'm just going to pop through this one. This is sort of an area where he thinks maybe perhaps if there is any debris to be found, that the debris field may have touched in this area. Again, this would be really hard to determine. It would require quite a detailed search. But hey, if you're interested, these are where the reports have come in of people and areas that saw it. So it was fairly widespread. Seemed to have come in over Quebec, headed towards Ottawa, where it disintegrated. Perhaps if he can look at some more footage in that, we can get an estimation of the altitude of the actual burst. But again, that's a fairly complex analysis, and there may not have been any debris that reached the grounds there. So, Fred, I hope I did some justice to your observation. A cool observation. I'm glad you caught a piece of that. All right. Next up, Jim. Are you with us, Jim? There you are. There you go.
Okay, so I'm going to be showing you some images I took with the Lunt, a 60 millimeter H alpha scope. And these are stacked images, stacked and auto-stackered, and then post-processed in IMPPG and Affinity Photo 2. So this is a monochrome image taken August the 7th. And note the active region in the bottom right of the photo with the lighter surface areas of high magnetic energy called plages surrounding the two sunspots. Now, sunspots are often occur in pairs of opposite magnetic polarity. Magnetic field lines loop back into the sun with one sunspot marking where the field lines emerge, and the other where they re-enter the solar surface. And here is a close-up of the prominence that you just saw, and you get a sense of how the plasma energy is moving at that particular time. On August 31st, the seeing was quite good, which is rare around here. I had the opportunity to take this image showing two active regions with huge lengthy filaments to the right. Filaments are prominences seen against the solar disk. And even though we can't see the magnetic field lines per se, we know that the plasma follows its path. So notice how the solar surface pattern changes in the vicinity of sunspots, active regions, and filaments. And here is a close-up of the region that I'm speaking about, and I've deliberately colorized it to enhance the detail a bit more. The thin filaments surrounding the sunspots look almost three-dimensional. And lastly, here's a solar animation taken a number of months ago. It goes in a forward direction, then repeats, so you see the action as it truly appeared. The prominence is pretty active, as you can see. It kind of almost reminds me of a tornado. Now, in the beginning of the animation, you'll notice in the central right part of the solar disk, there appears to be a coronal loop in action, where the plasma emerges from the solar surface in one area and loops to another area of opposite magnetic polarity. Anyway, that's my guess, and you should be seeing it right now. Well, I'm done. Thank you very much.
Thank you, Jim. Andrea, are you still with us online?
I am. These are I have to say, Richard, you have picked just some really wonderful challenge objects. Thank you so much for your effort every month to do this. Although these two galaxies have such similar numbers, the 7.4 and the 9.7, that all my numbers got all mixed up and my little dyslexic brain couldn't get them straight, but I think I have them straight. NGC 7479 is the Superwoman galaxy because of the S shape, and it's quite a lovely galaxy. The other one we've already seen, Bob has already taken an image of this. It's a beautiful galaxy far, far away, but we see it through some beautiful dust lanes. Galaxies are very small, and for that reason, they are really easy to image with a long focal length telescope. So I used my Celestron C11 Schmidt-Cassegrain with a 0.7 reducer. I use the ASI 2600 monochrome camera, and these are LRGB. I think I did one night of the spiral galaxy, and the other one I did maybe 2 nights. Next, please. This is the transit of Titan. Rick already explained it really well. It was a night of terrible seeing, and this was the best image I could get. Even then, my shadow is quite smudged, and I'm not entirely sure if I have a planet and a shadow or just a smudge. But in any event, it was a beautiful thing to see, and Saturn is a beautiful planet. Next. This is the blue snowball, which is a planetary nebula, NGC 7662. It's a really tiny object, as most planetary nebulas are. This was shot using narrowband filters. I did, I think, 1 night of oxygen, filter only, and then a whole other night of hydrogen, and then I combined it in a false color configuration, HOO. It really is very cute and very blue. And yeah, I was quite happy to get it. I've always wanted to get it. There actually is surrounding it a very faint O3, visible in O3 shell of material that's been ejected, but I have to process the image a little differently, and I haven't done that yet. So next. So this was a crazy night, actually. It was a very unexpected aurora. The data did not look particularly interesting, but I went out anyway, because, you know, why not? And I ended up running into a family that there was a couple there with their mother, and they had never seen the aurora. And this was a kind of a crazy aurora. It was visible to the naked eye and visibly flashing and bright and pulsating in the horizon, which is something I hadn't seen in a very long time. So I did a little time lapse. It's a little jumpy, but it was quite a nice show. So can you press play, please, Chris? I don't know if you can hear my dramatic music, unlikely, but what I loved about this show is there was actually some real cinnamon roll spirals in it, something that I haven't seen since Alberta. And it was beautiful in the camera and beautiful visually. And of course, we've had aurora for the last, 3 times this week. So, and more flares are going off. So keep your eyes open. Thank you.
There we go. I just have one observation for you tonight. It's an interesting one, though. It's certainly a new one for me. Earlier this week, I was up doing some camping on Cedar Lake, which is in northern Algonquin Park, near Brent, actually not far from the Brent meteor crater. And so I'd been up there for a bit with there's no cell phone or Wi-Fi or any such thing. You'd have to have a Starlink. So I wasn't aware that there was anything brewing on the night of September the 29th. I originally had set up my equipment to image the Milky Way because the moon had gone down and it's very dark up there and like 0 lights up there. But as I was setting up my equipment, I noticed I could actually see this. I could see a streak almost at 90 degrees away from the Milky Way. And I thought, like, is this my eyesight going or what is this? But as it turns out, this was an unexpected auroral display. I don't know if folks saw it here. It peaked at around 1 o'clock in the morning, morning of September the 30th, I'm sorry. And reports are that not only was there an aurora, which I'll show you here in a moment, but that red streak that you see there, it was either, some people thought it was the Steve phenomenon, but it is actually probably what we call a SAR arc, which is a stable auroral red arc of material. It's not an aurora, and it's typically quite faint. The camera really actually picked it up quite interestingly. And it was apparently, from reports a different part of the country, there was a Steve visible as well. There was this SAR arc, and as you'll see in a minute, there was quite an auroral display. From where I was camping on Cedar Lake, I had no view of the northern horizon. This is looking basically to the southwest, and as you'll see with the aurora, it becomes quite active. So I have no idea how active this actually got if you're looking towards the north, where they're typically much stronger. But I'll let it roll, and you can see I haven't processed. This is basically stuff that I just shot, and I haven't really had much of a chance to process anything. So the whole sequence I'm going to show you, I left the camera brightness adjustments as they were, so you get a feel for how bright this thing actually got, because it was weird. I was photographing the Milky Way, and then I see the arc here. and I see that over a few minutes, it's moving as a celestial thing. But then I get this wash of light coming in from the bottom right-hand side, which was the aurora itself. So I'll let this roll. Thank you, Chris. You can see it just obliterates practically the Milky Way as it zooms in there and washes out most of the SAR ray there. And then I had to switch perspective. I had to move the camera because I noticed that as the SAR arc was starting to fade, the aurora itself was really picking up some speed and some intensity. If I could just place my camera a little bit further towards the north. Unfortunately, I was already on the water's edge there, and I had to put my tripod out in the lake a little bit, but I did manage to catch it. I still have a few trees in the way there, but you can see the aurora was super active. It was quite an impressive display there. And as I say, this is a first for me. I'd never seen a SAR arc before, so hey, never too old to learn something new. Thank you, Richard.
Okay, so this is the challenge constellation of Pegasus, and you can see the square, the great square of Pegasus is quite prominent in the eastern sky just after sunset these days. There's the lines of the constellation there. And then we've already seen some pictures like this before, M15 right by Pegasus's nose, a nice globular cluster. The Superwoman galaxy, as we're supposed to call it now, except this is a straight-on view without any mirrors in there, so it's a little bit backwards. And then this is a very wide field view of 7497, and you can see the extent of the nebulosity around this little galaxy in the middle. So it's a very fascinating area to take a nice long exposure. And this was from North Frontenac, so the background sky was really, really dark. Zooming in on it from, I think this was from FLO, I didn't get quite as much of the nebulosity, but then you can see that the galaxy itself is a very interesting one. It's quite a complicated structure in itself. And then while I was out in North Frontenac, I took the opportunity of a beautiful south horizon to get one of the larger planetary nebulas in the sky. This is the Helix Nebula, which is NGC 7293, or also known as Caldwell 63. So I really recommend it. If you've got a nice view to the south, this is a wonderful object to take pictures of. It's so large and spread out that you don't really see much in the eyepiece. And then just Monday night, I got my last picture of Ceres. So this is quite an extent of from the August 27th all the way up to September 29th. And Ceres has been moving right across the northern part of the constellation Cetus. So those were the challenge objects for this last month. Thank you all for participating. So had a lot of people on the Discord server showing pictures of these various challenge objects as well. So for this next month, move a little bit farther towards the North Pole, and you'll find the constellation of Cepheus. It looks very similar to a child's drawing of a house. So it's not a very bright constellation compared to the one next door, Cassiopeia, which is down here in the corner. So it's sort of in between Cassiopeia and Polaris here. You'll find Cepheus. In a dark sky, it is fairly easy to find, but the nice thing about this constellation is it's really full of interesting objects. There's a lot of stuff going on up here. Now, we've also had some of them as previous challenges in previous years, so I've tried to pick a few new ones. And for the second level challenge, I thought it would be a nice idea to try out another variable star. And this one is a very interesting and important star. It's Delta in the constellation Cepheus, which is not part of the main house shape, but it's just off to the side here. But it is a fairly bright star. And the really interesting part of it is a pulsating variable star. And it's the one that is the basis for the distance scale that we use out to the galaxies. Because Cepheid variables, of which Delta Cephei is the prime example, pulsate at a pace that is proportional to their absolute brightness. So if you can see a Cepheid variable and measure its pulsation rate, you can actually figure out how bright it really is. And then by comparing that with how bright it seems to be, how bright it appears in the sky, you can then calculate how far away it is. And that's what was done back in the early 1900s to actually find the distance to the Andromeda galaxy, because they actually could find some Cepheid variables in that galaxy. They were very faint, but they pulsated in the same pattern as the ones we see in our own galaxy. And so we now could figure out how far away a galaxy is. So your challenge is to see that variable and try and figure out how it is changing. Can you see the changes? That's how it was first discovered, just by looking at it. Or, as I'm trying to do right now, figure out the latest software for measuring it in your photographs. There is a package that was just put out earlier this year, 2025, that adds on to PixInsight if you're using that software. And it, by a single click of the button, supposedly, you can measure the variations in star magnitude in your images. So I'm trying that myself, and I offer it as a challenge to the rest of you. See what you can do with it. For the other items, there's the Wizard Nebula, NGC 7380. And then, as the most challenging part, there's a very, very faint area of nebulosity. It's close to a cluster 7822, but the nebulosity itself has the label LBN 581. So just going back to the map, the Wizard is fairly close to Delta, and this other challenge object is down here, sort of halfway between the roof of the house and Cassiopeia. But all through this area, there's a lot of very interesting nebulosity. So wide field would be a way to go on that. Okay, so those are your challenges within Cepheus. And for our solar system challenge, we've just seen the transits of moons on Saturn. Well, what's coming up this month is a lot of double moon transits on Jupiter. So check out your Observer's Handbook or Sky and Telescope magazine for this month, and you'll see what dates they're on. There's I think about 4 or 5 of them happening this month. So see if you can get some nice views of moons on Jupiter. Thank you.
Thank you, Richard. Actually, I'm going to speed through some of these because we are terribly late. We have an FLO Star Party for members only coming up on October the 18th, so we're crossing our fingers for some clear skies. We've had a mixed bag of success with the weather, with the skies, but hopefully, well, we've got 3 opportunities left for the rest of the year, so hopefully we'll luck out with that. Estelle's pick of the month from the library is the Solar Astronomy Handbook, and I notice a lot of there's quite an increased interest even within our group on solar observing, so you may want to check this out. Information, just general club information, who's responsible for what. You can read the names there as well. And yeah, thank you for coming. We've had an audience of 90 folks today, 48 here at Chasm and 42 on Zoom. And I thank all the organizers who spent their time and their energy on providing us with wonderful presentations and very nice imaging. If you have any comments at all about comments or ideas, send them to me at meetingchair@ottawa.rasc.ca. And for those that might be interested, we have our usual post-meeting meeting at Liam McGuire's at 1705 Saint Laurent directly after this meeting. So thank you for coming. Clear skies for the rest of the month. Enjoy the nice warm weather. We're supposed to get like summer again for the next 2 days. 28 degrees, they're saying, maybe breaking records on Sunday and Monday. So we'll see. And just a reminder that the next meeting is Friday, November the 14th, same time, same place. It is the second Friday of November in that month. Thanks for coming, and a reminder, the rest of the museum is closed as you make your exit. Take care, be safe, enjoy.